Okay. All right. Welcome everyone on the recording. So this office hour is to go over the week 4 conjecture. And this is the first conjecture that it really works to do a proof by induction with, because the proofs you guys have been doing have been focused on equivalence proofs. And a lot of the algebra is the same, regardless of whether it's an equivalence proof or a induction proof. But the structure of the proof is a little bit different. So I was thinking maybe before we jump into the conjecture, I want to show you an example of what an induction proof looks like. And then we'll talk about how to specifically do the induction proof for this conjecture. Before I jump into that, though, does anybody have any questions or anything like that? Okay. Let me share my screen then. So the induction proof I'm going to share with you, like the example, is available in the assignment. It's linked in there. It's the example induction proof from the orientation meeting. So if you want to reference it as you're writing your proof, you're welcome to look at that. But we'll go ahead and look at it together right now. So this is not conjecture 4. This is one that I made up during our orientation meeting as an example. And as you look at these images, it's relatively easy to see what the pattern is. You have like one square and then you add 2 squares onto the ends, and then like you just keep doing that with all these images. So like image 3 has an additional 2 squares compared to image 2, and so on and so forth. And we talked about in the orientation about how we could predict, like based on the number of squares, how many squares would be in the nth image. And the formula that we came up with was 2n minus 1, because like in image 1, so in the first image, you do 2 times 1 minus 1, and you have 1 square. In image 2, if you do 2 times 2, that gives you 4 minus 1 gives you the 3 squares. Or image 3, you'd get 2 times 3, which is 6, minus 1, which gives you these 5 squares. So that's the conjecture that we're trying to prove in this example induction proof. And we can state it concisely with this algebraic notation. If I say that the number of squares in the nth image is going to be represented with this symbol. So basically, it's just like a shorthand way of writing the conjecture that I wrote in English words right here. Is everybody good with that notation? And the way that you read that out loud is f of n or f sub n. And you can also, like, this is usually the notation that mathematicians use when we're doing like a sequence that has a pattern. But it would also be accurate to write it like this, if that's easier for you guys to type. I put it in the chat, because it's basically just saying that it's a function of n. So that works as well, as long as you remember that that's function notation and not multiplication. So that's the conjecture. And when you write your induction proofs, make sure you state your conjecture really simply. And you also want to make sure that your description of the nth image is, it's called an explicit formula, which basically means like you could easily calculate how many squares there are in like the 100th image, and you don't need to know the 99th and the 98th and the 97th numbers to be able to find the 100th image number. That's what an explicit formula means. Like you could just, like in this case, if I wanted to know how many squares were in image 100, I would just do 2 times 100 and subtract 1 to find that there's 199 squares in this image. So once you've started your conjecture, or once you've stated your conjecture, an induction proof always has 3 steps. So there's the base case, the induction step, which is where the bulk of the work is, and then there's the conclusion. So the base case is basically just proving that your formula works for the very first image. So you say, okay, in image 1, there's 1 square. So we say there's 1 square, and therefore my conjecture is true for the number of squares in the first image because, and I substituted in a 1 because it's the first image in for n, and I show that my formula gives the same number of squares as the picture does. So the base case is really important logically. Like it's really easy to prove because you just plug it in for the first image. But it's really important logically because the induction step says that if you assume that it's true for the n-1th image, you use that assumption to prove that it's true for the nth image. So basically you say like, okay, I want to look at like assuming that my formula works for the image right before, whichever image I'm looking at, I want to make sure that that implies that it's true for the nth image. And the reason why you do that is because this proves it for an infinite number of images all at once. Because it says, okay, well, if it's true for the first image, which we proved with the base case, that's why you have a base case, then that implies that it's true for the second one. And that implies that it's true for the third, and the third implies it's true for the fourth and the fifth. And literally, because you did it generically, where you assumed the n-1th image or the conjecture was true for n-1, if you can prove that that implies that it's true for n, it proves your conjecture for like all of the counting numbers, like up to infinity. That might have been like a lot of mathematical jargon all at once. So could someone maybe restate in your own words what I just said about like the principle of induction? Or if you don't know how to say it, maybe ask a question about which aspect of it doesn't make sense.
So I guess what you're saying is we just put use your same wording but put our own injection in there.
You could, yeah. I do want to make sure though that you guys understand the principle of what you're doing, that it's not just like copying down my work, but you understand what it means. Um, so I can like could you restate it in your own words? Like what I just described? And if not, like that's okay. I can totally explain it again. I just
I
So-
guess he
Oh,
Oh, go ahead, you can do it.
I was just gonna say, what I understand is that when you are working with the n one term, so the term before the nth term, if I can take that, boy, I don't know how to say it.
that's
But
okay.
if I can take my n-1 term and plug it into the recursive formula as n-1. I don't know how to say it though. I don't know how to say that. Because is that the direction you go? Because you have two different formulas. You have the explicit formula, which is
Yep.
one that you don't have to know the before the previous term. But then
Yep.
you have the recursive formula, which is based on what's happening because of the previous term. So if you were to say, I know what both of those are, and if I take my explicit term and write it in terms of n-1, then I can take that and plop it into the recursive. And if it comes out as the same as the explicit, then that's what you're proving. But I don't know how to say that in words.
Yes.
Really.
Yeah, so that's the proof strategy. That's exactly it. So that's how you prove the induction step. And I love that you got that out of that because I hadn't gone into that yet. Yeah, so that's how you prove the induction step. How would you describe the principle of induction? And if needed, I can explain it again. Because like so the induction proof, the way you do it is just what you described. But like, why does that logically prove it for every image? Like, even like the billionth image. Like, why does proving this make it so that the conjecture is true for everything?
I'm not sure.
Okay, no worries. Does anyone feel like they got that piece? I can try to explain it in different words too, because honestly, this is a concept where it's like once you get it's like, oh, well, that's what it means, but it often takes a little while to get what it's saying. Okay, let me see if I can explain this in different words. Okay, so it's kind of like dominoes. You know how like if you have like a whole bunch of dominoes lined up, like if you hit the first domino, it like topples all the following ones. So the base case is like your first domino. So you say it's true for the first one. And then your induction step is the process of the toppling. So the induction step says if it's true for the first one, then it has to be true for the second one. And if it's true for the second one, it has to be true for the third. And if it's true for the third, it has to be true for the fourth. If it's true for the fourth, it has to be true for the fifth. And that logic continues infinitely because the n minus 1th term could be the first term, and you're using that to imply that the second term or like the second one is true because the 2 would be n in that case. Or you could also like it also proves that the 99th term implies the 100th term, or that the 1000th term implies the 1001th term. So like this generic assumption that the n minus 1th image, that assumption implies that the nth image follows your conjecture, that's like the toppling of the dominoes. Does that analogy help? And this is mostly like a conceptual thing. It's not like something you have to like put in your proof specifically. But it's like the reason why we prove patterns like this. So now that I've changed that analogy, could someone restate it in your own words? Because as I'm sure you guys have experienced as teachers, it often works better to have the students explain it to each other because they're at like the same level of understanding. So their way of explaining it helps everyone understand. Would someone like to restate that? Yep, exactly. In the chat, they said, so basically it's working through each image and proving it works for each step and therefore would work to the end. Yeah, and it's like, you don't have to go through and say like, oh, it's true for 1 and it's true for 2 and it's true for 3. You just prove that it's true for 1, that's the base case. And then you generically prove that if it's true for the term before any term, that means that it's true for the term itself, like the nth term, because that topples all the dominoes. Yeah, Amy, go ahead.
Dr. Willis, I wondered, because as I was trying to figure out how to do this, when I was looking at the recursive, I kept thinking about, okay, what is it that the previous term, what do we have to do to the previous one to get the next one? And so that the recursive formula tells you that. But then if you don't know what the previous term is, then you're looking at, okay, what am I doing to the input to get the output? And so then kind of like a function, right? And so then my feeling was if you can take the two expressions, and that's why I thought if you take the expression that defines it according to a previous term, if you can plug that into the one that defines it as a function, to me that's where you get the, I don't even know how to say that, but to me that makes sense instead of I don't know if I take out all the n minus ones and all that, but if I'm just saying the previous step, if I know what I have to do to the previous term to get the next term, if I know that and I can see that, but I also know what I have to do with the input, the current term in order to get the output that I want on that current term. if those two match, that seems to prove it to me, but I don't know that
Yep.
that's exactly what you're saying with the dominoes effect, but that's kind of how I see it. I'm not sure.
Yep, you're exactly right. Yeah, and I like your languaging, so I think I'll borrow that. So instead of saying the n-1th term, I'm going to say the previous term, which just means whatever term we're looking at, it's the one right before it. So mathematically, that's the n-1th term, but I'll say the previous term because I like that languaging better, and I think it helps it not feel so overwhelming. So, and then I'll say the current term for the nth term. So the current term is whatever nth term we're working on, and then we've got the previous term. Okay, so I kind of explained the theory behind why a proof by induction proves it for everything, because like you wouldn't want to go through and plug in numbers all the way up to infinity because there's an infinite number of numbers. So like you've got to do something that proves it more concisely. So I kind of went over the theory of it. So now let's look at the actual details of how this is proved. So we state our conjecture, and our conjecture should be an explicit formula where it's just like you said, a function, where you can plug in whatever number of term you're looking at to figure out how many squares would be in this pattern. Then the base case is like the first domino. And so you have to prove that this formula works for just the first picture in this case. So you go through and prove that, and that should be pretty simple because it's just as straightforward as saying, in the first image, there's one square. My formula gives you the number 1. So base case is always really easy. Then you say, I'm going to assume that my conjecture is true for the previous image of whatever image I'm looking at. So that's the n-1th image. And since I'm assuming that it's true, I can just state my conjecture was that the nth term is 2 times n-1. So if I'm assuming it's true for the n-1 term or the previous term, rather than plugging in an n, I'm plugging in an n-1 into that spot in my conjecture. Is everybody good with how this assumption translates to this mathematical statement? So like my statement or my conjecture is that any term is the number of squares in that term will be 2 times the image number minus 1. So if this is true for the n-1th image, I'm just putting n-1 in for this n spot. So this is my assumption. So I'm just assuming this is true. And that's the process of induction. So I assume that this is true. And my goal is to prove that for the current term or the nth term, that this is true. And so in order to do that, like you said, Amy, you need to have a way of describing the nth term that uses the previous term. So that's the recursive formula, where you have to know the one right before it to be able to find the next one. And in this specific example, because each image has 2 more squares than the previous one, this is how I would describe it. On the pattern that we're doing for the week 4 conjecture, it's a different pattern, and we'll talk about what that recursive formula would look like. But in this case, it's just you add 2 to the previous one to get the current one. Is everybody good with that part? Yes, no, what, any questions?
That makes sense so far.
Okay. So again, my goal is to show that this, the nth term or the current term, is equal to my conjecture. So I'm going to use my assumption that the term right before it, or the previous term, equals this stuff, and you basically just substitute it in. So to get from here to here, you substitute this in for the expression that says you take the previous term. And then from there, you just like either distribute, factor, cancel out terms, basically do the stuff we've been doing on the last few conjectures. until you get the form looking like what you want your conjecture to look like. So in this case, I distributed the 2 to get rid of the parentheses. Then I combined these like terms, and since -2 plus -1 plus 2, like the -2 and +2 cancel out, you end up with just the 2n minus 1. That is my conjecture. And so because my assumption my assumption that the previous term follows my conjecture implies that it's true for the nth term, then I'm done with my induction step. And the conclusion basically summarizes the domino effect idea. So the way I word it, and you guys are welcome to word the conclusion in a different way, but it's basically describing the domino effect. So I said, because my conjecture is true for the first term, and the assumption that it is true for the previous term implies that it's true for the current term, then the fact that it's true for the first term implies it's true for the second term, which implies that it's true for the third term, which implies it's true for the fourth, and so on for every single possible term. Therefore, my conjecture is true. So the conclusion is basically just explaining the domino effect of why the induction step proves that your conjecture really is true for everything. So that's an example proof. Do you guys have any questions on that before we go to the conjecture you guys are proving? Okay. Let's go over to that. So you look at the project guide. I'm mostly just looking at the pattern. So an induction proof always requires an explicit formula, which is going to be your conjecture statement. And then it also requires a recursive formula to help you do the induction step so that you can use the previous term to prove the next term. So usually recursive formulas are easier to find because those are the ones where it says like, you do this to the previous term to get the next one. And then you do this to the, like, it's the one that usually is easier to find. So let's look at this and see if we can describe it. So if I'm looking for, let's say, like if I want to get from image 3 to image 4, what's the pattern of what you would do to image 3 to get image 4? Okay. Yep. And Melissa, nice job on catching the general pattern. Yep. So to get to image 4, you would add 4 boxes. If you wanted to get to image 5, what would that one be?
All right, you stay here.
Yep, add 5 boxes. So if you want to get to the 6th box or the 6th image, you would add 6 and then you'd add 7 and so on. So if I wanted to write a formula, the way that I would write it, and I'm going to write it in function notation because I can't do the little subscript thing in the chat. So I'm going to write it like this. And then, let's see, how do I want to, I'll do like a ... that I want you guys to fill in. So the nth term, whatever n is, what do you do to the n minus 1th term to get the nth term?
N times n plus 1 over 2.
Oh, I think, yeah, you've got the explicit one, so we'll use that in just a second. This one's looking for like, what do you do to the previous term to get the next one? So Amy, you said that it would be f of n equals f of n minus 1 plus n. And we can test this out because we can say, okay, well, what if I'm trying to find image 3? Well, that would mean that I'd be looking for image 3. And according to the formula I just put in the chat, we would have the number of squares in image 2 plus 3, which that is true. To get image 3, you do take the number of squares in image 2, and that gives you 3. And you could plug in some other ones to make sure. But it is always good to double check and make sure that you didn't like offset it by 1, because sometimes I do that, where like I didn't describe the pattern the way I thought I meant to. So, but that one does work, because for image 4, you would take the number of squares in image 3 and add 4 more to it. Is everybody good with how we got that recursive formula? And again, the recursive ones are not like, they're useful for the induction process. They're not useful in general though, because if I asked you to find how many squares were in the 100th image, you would have to know how many were in the 99th image to be able to add 100 to it. So they're not very useful in general, but they are helpful for proving induction ones. So we've got our recursive formula. And now we need to come up with an explicit formula where you can just plug the number in. So I think it was Tess. Did you have one for the conjecture?
N times n plus 1 over 2.
Okay, let's try that out. So this is the prediction, and I guess I should have written it as f of n equals that. So this is our conjecture. And if we try that out for some of the ones, just to make sure that our conjecture works for our pictures so far. So this isn't part of the proof. This is just us noticing patterns. So we haven't actually started the proof yet. We're just trying to decide what our conjecture would be. So maybe if I want to do it for the 4th one, I'll say f of 4 equals 4 times 4 plus 1 would be 5 divided by 2. That gives us 10 because you get 20 divided by 2. And if you count up the squares in image 4, there are 10 of them. And you could try it for the other ones. But I've done this before. So, and probably you guys tested it out as well. But this is the correct conjecture. So the conjecture we're trying to prove is that the nth image is going to have n times n plus 1 over 2 number of squares. So that's the conjecture we're trying to prove. And then once we've stated the conjecture, so we've stated that the nth image is going to have n times n plus 1 over 2 squares, what would the next step be based on what we looked at in the previous, or in the example proof? Remember, induction proofs have 3 steps. So we've stated our conjecture. Now we need to start on step 1.
The base case.
Yep, exactly. So for the base case, why don't you guys try typing it out in the chat, like what that proof would look like. And it's okay if it's not like super polished or whatever. Okay. Yep, perfect. Yep, so since you're wanting to prove it for the first case, B Murphy, you would put a 1 in the like f of n spot because you're not proving it for the nth term, you're specifically proving it for the first term. Yeah, no, you're good. Like you got the basic idea. I'm just like kind of polishing the notation for it. Yeah. Yep, so Anita, the one that you put in, that's the conjecture we're trying to prove. The base case is specifically proving it for the first image. So like if we go back to the example one, the conjecture is going to be that one that you put in, Anita, and then the base case is where you say there's however many squares there are in image 1, and my conjecture is true because my formula gives me a 1 when I plug in a 1. So that's the base case. And the base case should always be pretty easy to prove because you're just plugging in a 1.
Thank you.
Yeah, of course. Let's see, there's someone, oh, this was you as well, Anita. You said, I can see the pattern and write what's happening in words, but could not come up with the algebra to write it in. So that's natural. And your students, when you guys do pattern finding at their level, they're going to have the same thing where they can see a pattern, but they don't know how to put it into math language or into math sentences. So that's like part of, I guess, teaching the process of doing conjectures is to help be able to translate the pattern into like a math sentence. So we're going to do all of that today. So don't worry about that part because I'll help you guys take the patterns that you're noticing and put them into words. Okay, so going back to our one that we're proving. So we've got our conjecture, we've got the base case. So now we look at the induction step. So the induction step, the first part of it is you need to assume that your statement is true for the n-1th image. So go ahead and type into the chat. If we assume that it's true for the n-1th image, what does f of n-1 equal? Based on what our conjecture is. And I'll restate the conjecture up here because I forgot to write that in. So
Wouldn't we want to put a number in instead of the f and then the n-1? Wouldn't we want to put in like a 3 or something?
you can do that to help you understand it, but if you put in a 3, this whole process would only prove it that it's true for the 4th term. And we don't want, like, I mean, that is great, like it is true for the 4th term, but we want to prove that it's true for an infinite number of terms. And so that's why we're doing it generically with n, because it will apply for the 4th term or the 100th term or the 101st term or the 102nd. Like it will apply for any term.
Okay, so then wouldn't it be what we wrote before, where the f of and then the n-1 parentheses plus n? Let me write that down.
Yeah, I think you got it.
Okay, cool.
So let's see, Anita. Okay. Michael, I'm not sure. I'm not sure about that. So I'm gonna like notate it on the screen so it at least shows up on the screen. I think the chat might be saved separately, like as a separate file, and I can attach that. Okay, that's good to know, Leslie. Okay, I will make sure I'm writing it on the screen as we talk. Okay. Yeah, so you guys have got the recursive formula, which we'll use in just a second. So I'll write this down. So the recursive formula is that f of n equals f of n-1 plus n. So that's the pattern. It's like that you're adding n every time. But we want to be able to replace this with like something that only involves n's. And that's why this assumption is important. So we're assuming that the conjecture is true for the n-1th image. And we're going to use that assumption to replace this. So our conjecture is that any term is that term number times the term number plus 1 divided by 2. So if I were to plug in n-1 for the term number, what would that look like? Yes, exactly, Amy. Perfect. Yep. So it would look like n-1 times n-1 plus 1 over 2. And I'll kind of color code this so you can see it a little bit better. So this n got replaced with an n minus 1. This n also got replaced with an n minus 1 because I'm assuming my conjecture is true for the n minus 1th term. Does that make sense? Is everybody good with that step? So this is the assumption. And then I'm going to use that and substitute it in over here. So when we do that, and like that's basically the hardest part is you like assume it's true and then you plug it in. And from there, it's basically just simplifying it and making.
That blue is the recursive formula?
Mhm.
Okay.
Yeah, so that was like when we first started looking at the pattern, we found the pattern where like to get to the third one, you take the number of squares in the second one. Let me actually scroll up a little bit so I can point at it. Oh, dang it, I didn't know my annotations would move too. Sorry about that. So we talked about how like to get from image 1 to image 2, you add 2, but then to get from image 2 to image 3, you add 3 squares, and get from image 3 to image 4, you add 4 squares. So that's where the blue one came from, is the observing the pattern that you always take the previous one and add whatever image number you're on. So that's most of the hard work. The rest of it is just rearranging it to make it look like what you want your conjecture to be proved. So I'll do this in purple. So when we plug that green stuff into the blue one, we get that f of n equals n minus 1 times. Can this stuff be simplified to make it a little bit easier to work with? Like if we have n minus 1 plus 1, what would be another way of, yeah. Yep, you could just multiply that by n. So that is a simplified version of the green stuff. And then we add n to that because you take the previous term. So this is representing the number of squares in the previous term. You just add n number of squares to that. So this expression describes how many squares are in the nth term. And now what we need to do is we need to make it or prove that that is equal to this. So to do that, notice that we have like this plus n, and essentially this is like adding fractions because you have this fraction plus this fraction. So what do you need in order to add fractions?
Same denominator.
Perfect. So what would the common denominator be in this case? Perfect. Yep. So that means that I could rewrite this from the purple one to the orange one as n minus 1 times n all over 2 plus 2n over 2. And once you have common denominators, you can add them together, right? And it might also make it a little bit easier if we also use the distributive property to make it so that we don't have these parentheses. Because ultimately we do want parentheses, but we want the parentheses of n times n plus 1, not n minus 1 times n. So if we write this as n squared minus n plus 2n all over 2. Is everybody good with that part? So like I just distributed this to get this part. Okay, so,
Would that, oh, sorry,
Oh, go
one
ahead.
quick question. Would those
Yeah, go
need to
ahead.
be 2 steps? So like do the distributive property and say I'm doing this, and then like have a line and then say,
Mhm.
okay, now I'm putting them together.
Yep.
Okay.
Yeah, so, and I mean, yeah, probably it would be better to do it in 2 steps. I did it in one, like, because I multiplied by 2/2 with the n term, and then I also distributed at the same time. Yeah, and you could actually, if you wanted to, you could also simplify this, because like we had to do like the -1 + 1 to get this, or the n by itself. So like we simplified that, so you would need to like justify that, and you could also distribute at that same time. You could say, then I can distribute the n, and you could do all of that for the green part before you substitute it into the blue part if you wanted to do it that way. Or you can do it after you substitute it, and it doesn't really matter. Okay, so we are at this pink step right now, and our ultimate goal is to get back to our conjecture. So any ideas of how we could simplify the pink stuff to make it look like our conjecture?
We'll take the n out.
Okay. And if we take out an n, like, and you're saying take it out of everything in the top?
Yeah, because there you could then you'd leave n -1 + 2.
Perfect. Okay. And then we're almost there. And the last step is super easy. Because the black stuff almost looks like our conjecture. What's the last step we need to do to make it look like it? Yep, perfect. Combine the like terms, and that would give us n times n + 1 all over 2. And technically, you could also combine like terms at this stage. That would be another possibility, because if you have a negative n plus 2 n's, it's negative or positive n. So you can combine like terms either before or after factoring. And then you did it. That's it. Because the induction step is where you assume it's true for the n-1th term, and then you use that to prove that it's true for the nth term. And then the last step is just concluding it, which is like describing the domino effect that we talked about earlier, about how assuming that the previous term is true implies that the next term is true, that makes it true for an infinite number of numbers. So, what questions do you guys have about that?
Just one quick question. When we write it up, I was noticing your document is in a PDF. Would
Mhm.
you be able to make that be a Word document so we can use, like, have the pictures and stuff on our conjecture that we submit?
Yes. Oh, maybe. I don't know if I have it on this computer. It might be. No, I think I do. I think I do have it on my laptop. So yes, I can upload that right after we finish this up.
Awesome, thanks.
Yeah. Any other questions? Okay, awesome. So, just as a reminder, as you go through this part, so like the purple to the orange, the pink to the black, we talked through what the justification was, like finding common denominators, distributing the n, factoring out the n, like all of that stuff. In your proofs, just make sure that you explain what the reasoning is from each step to the next. So we talked through it, but I didn't type it out. So just make sure you
So
include that.
on the one form, which I'm trying to look over, it says, you said there's 3 steps, but on the paper it just says step 1 base case, step 2 induction
Oh,
step.
did I miss the conclusion part
Yeah,
that get cut off the bottom. Okay.
yeah. So step
I
three,
mean, basically the conclusion is the same every time. Like, that's the process of induction, is you always like say the previous term implies the next one, which implies the next one, which implies the next one. So, yeah, so you guys can kind of like just restate like my conclusion for the other one that we were looking at, the example one. Just
Okay.
restate it in your own words. Like however it makes sense to you to describe that domino effect. Because there's not really anything like mathematical in it. It's just saying like this proves the conjecture. Jackie, yeah, totally. Yep, absolutely. All right, cool. Well, that's it. So I will post the Word document as soon as I've finished this meeting. And I don't think and then I'll also post the recording for this as well. Is there anything else you guys want me to include?
Dr. Willis, this is
Mhm.
Anita.
Yeah.
This has nothing to do with the conjectures, but I was just wondering if you could remind us what's going to be on the final. I remember something from the first meeting, and I thought you said it was the homework,
Mhm.
but I didn't know if there was more than the homework on the final.
Yeah, so the homework is the best thing to study for the final. So it's not like I'm going to take the exact question off the homework. But
Right.
there'll be similar types of questions. So like if the homework is like draw a set model for -3 + 5, like your final might be like draw a set model for -2 + 7 or something like that. But the whole like
Okay.
all of the final is based on the homework. So
Okay.
yeah, because the homework, I mean,
Thank
it's not really worth a ton of your grade. I think it's like 10%. So the final is kind of where you're assessed on whether you really understood the stuff on the homework.
Okay. Thank you for clarification.
Yeah, thanks for asking. I haven't written the final yet, so I'm not sure how many questions yet, but I will send that information out as we get closer. Usually it's like a couple questions per homework assignment, like 3 to 4 per homework assignment. Any other questions before I end the recording? And Jackie, I'll stay after and help you with the formulas as well. Actually, maybe I'll keep the recording going because that might be helpful for recording people as well. All right. Jackie, do you want to go ahead and ask your questions then?
Yeah. So, sorry, can you hear me? I don't usually talk.
Yeah.
So I guess, I mean, I can see the pattern in the picture just fine. And I know that like in the second box, we're adding 2 and then adding 3 and then adding 4 and then adding 5, etc. I just really am lost into how to write those formulas to where they're vague. I always want to put a number in
Specific
there.
numbers.
Yes, and that's where I got dinged on the week 2 homework too. And so I'm not quite sure what to do as far as making vague or just generalizing formulas that would fit with any number. Because I don't even know if I understand the language. I'm really trying to, but I don't know if I do. And so so I guess I understand I'm looking at the base case formula and I'm just like, I don't really know how, like, because I'm seeing it as like add 1, add 2, add 3, add 4, but like, why is it dividing by 2?
Yes.
I don't,
Okay.
I'm just,
Yeah. So there were some people who had that formula right off the bat, and I didn't go into how you would find that formula. So the pattern that you're noticing of adding 2, adding 3, adding 4, adding 5, that is the recursive formula, which is this blue one. Because
Okay.
that pattern of adding a certain number to the previous one, that requires you to know the previous one.
So that's function n equals function n plus, I don't know, the,
Yeah, and if you want to, you can read this using the notation Amy introduced, or the verbiage of it, because
Mhm.
f of n is the current term. The nth term, or the term you're looking at, is going to equal the previous term. So like, and you can put in numbers for n to help you wrap your head around the notation. Because like if n was 4, that would be
Uh-huh.
saying that the fourth one is the 4 minus 1th one, which would be the third one, plus 4. So like,
Okay. So the f of n would be the, did you say the current term or the,
yeah, so like whichever term you're looking at is the
Mhm.
previous term plus whatever term number you're on. So like if you're looking at the 5th one, it's the 4th one plus 5. If you're looking
Yeah.
at the 100th one, it'd be the 99th one plus 100.
Okay.
Does that part make sense?
Yes.
So
Yes, I mean,
that's the pattern you were observing. And that is not how you would find this formula. I'll talk about how you would find this formula in just a second.
okay.
But the
But I mean,
pattern you were observing, this is how you would put it in algebra notation.
so the one where you're dividing by 2, I want to understand that because
Mhm.
that's the one we kind of ran with, and that's the one I took all the notes on. And
Yeah.
so when we plugged the 1 in, so
Mhm.
f1 equals 1 plus 1 plus 1, and I know all that equals 3, and then
Yeah.
divide by 2.
Yeah. So let's pretend we didn't know that was the formula.
Okay.
So that is the formula we end up with, but let's pretend we didn't know it. What we're looking for is a formula that describes the number of squares, and we can figure this out by looking by writing out the numbers and seeing if we can find a pattern. So in image 1, we have 1 square. Image 2, we have 3. Image 3, we have 6 and 10 and
Then
15.
10 and 15.
And in the hint, I said if you double all the numbers, it's easier to see the pattern. And so this is where the other people just knew what the formula was because they'd been looking at it before class. And I probably should have done a better job of talking about how they found that formula. That was my bad for not going into where that came from. Because if we double these numbers, so I'll write these in a different color. So on image 1, it would be, it's not 4. So on image 1, it would be 2, because that's 1 doubled. If I double 3, it's 6. If I double 6, I get 12. If I double 10, I get 20. If I double 15, I get 30. Do you see a pattern in those numbers?
Okay, hold on. Sorry. Okay, so the first one we're adding 4, then we're adding 6, then 8, then 10, right?
Mm-hmm.
Yeah. Okay.
Yeah. And is there a pattern that doesn't depend on the previous one? Like, is there a
No.
way that you could predict what the, say, 10th one would be?
I'm sure there's a way. I would have to draw it all out. Um,
Okay.
mm,
So let's maybe approach it this way. Like, there's lots of ways you could get the number 2 or the number 6 or 12, right? You could get it with adding. You could, like, 2 is 1 plus 1, 6 would be like 3 plus 3, or 2 plus 4. Like, there's lots of adding possibilities. But let's look at multiplying ones. So like 2 can be written as 1 times 2, and 6 could be written as 2 times 3. And is there a way we could write 12?
And then
That
3
has-
times 4,
Mm-hmm.
and then 4 times 5, 5 times 6.
Uh-huh.
So every number would increase by 1.
Uh-huh. And what if I asked you to figure out the 100th one?
And I
What
know
would
everyone
be-
in the chat is going to be able to get it. I just don't
No, you're fine.
get it.
Take all the time you need. And I'm also like, this is also a learning experience for me. So it's not like, because like the goal of these conjectures overall is for you guys to stretch yourself the way you guys are going to be asking your students to stretch themselves at their level. So like me mentoring you through how to like look at the patterns, like that's the same process you'll mentor your students through. And I'm not perfect at it. So like if you're like, this would be a better way for you to mentor me right now, like take note of that because that would apply to your students as well. And also I'm open to feedback because this is my first time teaching this class. So it's not like I know exactly what I'm doing all the time. So feel
Dr.
free to
Willis?
take all the time you need. Yeah, Shelley, go ahead.
I just have a question. I can't, in the blue, what you have written, I can't
Uh-huh.
tell what it says. And so I think I'm getting confused on what we were supposed to start with versus where we're going because I actually don't know what we have written in the blue.
Are you talking about the blue that's like in the boxes with the images? Because we have a couple different
No, like
blues.
down below it where you were writing, I think it was the recursive formula.
Uh-huh.
I don't, because it looks like it's a -1 and I thought we were doing +1 divided by 2 at the recursive. So I think I got lost in that point somewhere.
Okay, I will put it
Can
in
you
the
just
chat
tell me
really
what
quick.
it says right there? Okay. Thank you.
Yes. All right. Okay, so Jackie, coming back to the question about 100. And we're just gonna look at the doubled number. Because it's relative, like once you find the doubled number, it's not too hard to find the pink number. Right? Because like you just divide by 2, which by the way, that's where this divide by 2 comes from. But like I want to look at how could we figure out what needs to be multiplied for the 100th term. And the key here is that we're looking for a relationship between the image number and the calculation that we're doing. So like in image 5, we did 5 times 6. In image 4, which is all covered up, we did 4 times 5. In image 3, we did 3 times 4. So for like the 100th image,
It would be 100 times 101.
perfect. Yep. And let's say we did like the 987th.
987 times 988.
Mm-hmm. Okay, now
Right.
what if we did the nth term?
Ugh.
We can do some more. Okay, what if it was the 16th term?
Okay, 16 times 17. So it would be, I know it would be n times oh, that's where the n times n plus 1
Mm-hmm.
comes in.
Yep.
Okay.
And the divide by 2 comes from the fact that these blue calculations are not what we're trying to find. We're actually trying to find the pink ones.
Uh-huh.
But we just doubled them because I gave you the hint that if you double all the numbers, it's easier to see the pattern.
Okay.
So that's where that came from. And that was totally my bad for not going through that. So it can be a teaching lesson as an anti-example. Don't just take a couple people who like know the pattern and assume everyone else knows where that came from. That was totally my bad.
Okay.
Does that
so
help?
okay, so now I can understand the Fn n times n plus 1 divided by 2.
Awesome. Yeah, so you need both of the equations. So you've got this explicit one, and the explicit
Uh-huh.
one is the useful one. That's one we're trying to prove. because that's the one where you could figure out how many squares are in the 100th one, which without having to know the 99th one. So
Right.
this is what makes the conjecture, but you also need the blue one, the one that like builds on itself, in order to prove the conjecture. So they're both necessary. But the
Okay, so
conjecture, oh, go ahead.
oh, sorry. So I'm looking at the n times n plus 1 over
Mhm.
2. And
Mhm.
then in the induction, we wrote down n minus 1 times n minus 1 plus 1.
Mhm. Yeah, that's
How do
because we
we
were,
go from that to that?
yeah, good question. So the n minus 1, instead of looking at the nth term, we're looking at the term right before it. So it's like
Okay.
n minus 1 is the number of the term we're looking at. So like if n is 100, we're looking at the 99th term. And we're saying that you would do 99 times 99 plus 1, which we simplified up here to just be like 99 times 100. Because
Okay.
I'm using the 99 example because you said that number, like putting it in number form makes more
Okay.
sense to you, but it applies to anything. So like if you were
Yeah.
looking at the 500th term, the n minus 1th term would be the 499th term. If you're looking at the 17th term, n minus 1 would be the 16th term.
16th. Okay. So if I'm looking at it, so let me just see if I can do this with like put some numbers into it. So if I'm looking at the induction formula that we wrote down, and I have an f n minus 1, so say I'm looking at the second and third term,
Okay.
or if I'm looking at the third, if I, n was the third term,
Mm-hmm.
or 3 or whatever, then
Okay.
n minus 1 would be 2, right?
Mm-hmm. Yep.
So that would be 2 equals so in the second parenthesis, I get the first parenthesis n minus 1, that would be 2, and then there's an n minus 1 plus 1. So that 2 plus 1, that would be the 3. That would be
So if you put in a 2 for n, or no, sorry, the 3 is, sorry. The 3
so
is
that
n.
so looking at that
Yeah, so
second parenthesis on the top, the n minus
Mhm.
1, that would be a 2, and then if we plus 1, then that would equal the 3.
Mhm.
To me,
Yeah.
that just seems like a really long way to say 3 or the third or the next term or whatever.
Yes. Yes,
Okay.
it is. And the reason
But
why you do it in this form is because, like, if you say n is 3, you can just plug in a 3 and you can simplify it. But if you want to prove that it's true for 3 and 4 and 5 and 6 and 7 and 8, everything all the way up to infinity, you have to do it with n's. And there is no other way to write like the previous term than using n minus 1. Like
yes.
if n is 3, it's easier to write 2 than it is to write n minus 1. But n doesn't only equal 3. It's also 4 and 5 and 6 and every number up to infinity.
Okay.
Does that make sense?
So
Because like you're
yeah,
trying to prove it for everything, not just a
yeah,
specific example.
yes. And this is a completely whole new way of thinking because I'm not a mathematical person at all.
No worries.
And so when writing step number 2 in assuming my conjecture, how would I explain it without putting in a specific number to like illustrate it? Because in my brain, I'd want to put in specific numbers to illustrate the point, but then I'm not sure how to verbalize that this is just a general formula that will work for any
Mhm.
terms.
Yeah,
So that
so
is
that
really getting stuck.
yeah. And if it helps you to put in numbers, you're welcome to do that, but you also have to make sure you have the generic one. So the way that I think of it is like it's in the assumption of it. So I have like so many colors up here. But this right here that I'm pointing to
Uh-huh.
in blue, that's
Yes.
our conjecture. Our assumption is that the conjecture is true for n minus 1. So basically, we replace all of these n's with n minus 1's. And that's why we have an n minus 1 here, an n minus 1 here, and n minus 1 here. So it's literally just an assumption. So like you don't have to prove that it's true. You're assuming that it's true, and you're using that assumption to prove everything else.
Okay.
So like the justification for it, if you wanted to put it in like an English sentence, is like you'd say, assuming that my conjecture is true for n minus 1, then f of n minus 1 equals all the stuff we wrote in green, because I can replace all of the n's in my conjectures with an n minus 1.
Okay.
And you can also, like, sometimes this notation can sometimes be helpful for like thinking through it.
Yeah.
If you write it like the green statement, if you put the n minus 1 stuff in parentheses,
Mhm.
sometimes that can, like, it's kind of like a lot of extra parentheses you don't have to have, but it can help like point out the fact that you're replacing the n's with the n minus 1's.
Okay.
Again, you don't have to do that, but sometimes that helps to like say this is specifically like getting plugged in here. I don't know if that's helpful or
Okay.
not for you.
No, yeah, I think I have a little better handle on it. And then I had a question on my week 2. I know it's kind of late for week 2, but I just wanted to ask. So the big problem on week 2 is that I showed examples with specific numbers. So when you say take out the specific numbers and do it in formulas, you just kind of mean replace those numbers with variables and give me a generic formula, right?
Yeah, and we can go through a couple of examples with that. I do need to clear my screen to be able to do that though. So does anybody have any questions about anything I have on the screen right now before I clear it? I know I have a couple people still in here. I will go ahead and clear all those drawings and open up a blank page.
Okay, let me just see if I have my
And remind me, was week 2, is that
homework.
that's the exponent one, right?
Yes.
Week 2 is exponents.
And let's see. Oh, rats. I don't. Okay. All right. Sorry. If you can just let me see if I have week 2 in my downloads. I'm on a Chromebook, and so they're.
I can
not.
open it up if you're okay with other people seeing it, or we could also do a breakout
Yeah, at
room.
this point, I don't care. I have no shame.
Okay.